you're happy.
Okay, you're cutting a little bit, Tim, but I assume that means that we are about
Sorry,
to start.
yes, start whenever you want.
Cool.
Yes.
So, hello, everyone. It's a great pleasure to have with us today, which actually is Thursday in the US, but Friday already in Australia, Dr. Dominic Verity. And Dom, I asked him for kind of nice things to say about him. So he says that he says he's a badly bad drummer. So he says, I'm a research mathematician whose side hustles include programming, electronics, incredibly bad drumming, and university governance, which I think is how he has been suffering more recently. As you might have heard, Dom and Emily have a book and I think, I at least invited Dom thinking that he could do a book tour, a Zoom book tour, and that's, I hope it's part of that. Now, his research interests lie in the mathematics of fields of homotopic theory, sometimes known as rubber sheet geometry, and category theory, a kind of theory of everything for pure mathematics. He is also active exploring applications of this work to the computer science of programming languages, and his most cited paper introduced trace monoidal categories, structures that have become a key component in modern accounts of iterative processes in traditional and quantum computation. He did mention that his closest mathematical collaborator is Emily Real from Johns Hopkins, and together they are responsible for developing and popularizing model-independent and syntactic approaches to infinite one category theory, I hope. I hope I can at least pronounce it. I'm not even sure about that, but I'm sure I will learn all about it in Dom's talk. So take it away, Dom.
Well, thank you very much, Valeria, and to the Topos Institute for inviting me to give this talk this morning here in Sydney. I'd like to start just by acknowledging the traditional owners of the land on which this talk takes place for me, although obviously not for everyone else. The Watamatical clan of the Darug Nation, whose cultures and customs have nurtured this land since the Dreamtime. And I'd like to pay my respects to the elders past, present, and emerging. So, of course, Valeria mentioned that we do have a book, and that she suggested that maybe this could be part of a virtual book tour, which wasn't something that I'd considered before. Although I'm sure that Emily has actually been on a virtual book tour for quite some time, because she speaks about these things much more frequently than I do. The name of our book is Elements of Infinity Category Theory, and it does indeed talk about model agnostic infinity category theory. So in other words, infinity category theory that isn't grounded in a single concrete model of what an infinity category is. And I'll come to explaining what that means as we go through the talk. Let me just fiddle with my screen here. And so, as I say, the technology never quite works when you want it to. So let me try this. The authors of this book are myself, Dominic Verity, and Emily Real, and you have some nice photographs of us there. I should say that in that photograph, Emily is playing Australian rules football, and people may not know that she actually represented the USA in various international tournaments in what is Australia's national sport, or one of our national sports, I guess the other one being cricket. And so you might say that we're partners in infinity crime, and I do hope that we continue to be partners in infinity crime for very, very many years to come. So let me just, in this talk, I'm going to make no particular assumptions that anybody knows anything about infinity categories. So for those of you who already do, you'll have to indulge me a little bit while I go through some of the basics. So maybe, I was kind of scrabbling around for examples that might illustrate why we might want these structures rather than just simply rushing in and attempting to define them. So maybe something that everybody would be familiar with is the notion of the fundamental group or the fundamental groupoid of a space. So if I'm given a topological space, then it's very natural to take points in that space and to consider continuous paths from one point to another. So here's my space. It's got a nice hole in the middle of it. And I've got a number of paths. I've got one here that goes from A to B, and I've got another one here, Q, which goes from A to B, and so forth. So I might look at all of those paths, and I might ask, what kind of structure does that have? Now, of course, one of the things that we do early on is we realize that there are various relationships that we have between paths. So we can certainly talk, I guess we could talk about equality of paths. Are two paths literally equal? But it actually turns out that a much more useful relationship is to consider homotopy. So homotopy is a notion where we consider not strict equality of paths, but where we consider, I guess, perturbations or continuous transformations of one path into another. So you might imagine that Q and R are related in this way. So there's a continuous transformation that moves Q and ends up with R, and that movement goes entirely through the space. So in this case, Q and R are homotopic relative to the base points, so those don't change. But of course, P is not homotopic to either of those because there's a hole in the middle of this space here that prevents that from happening. And so what we do is we create a thing called the fundamental groupoid. And the fundamental groupoid is a category, and it has, as its objects, points in the space. And as its arrows, it has based homotopy classes of continuous maps. So those are equivalence classes of continuous paths. And so in this case, Q and R would be in the same equivalence class because they're homotopic, but P would be in a different equivalence class. And then the way that we compose these things is just simply to concatenate paths together. So if we have one path from A to B and another path from B to C, then we concatenate those two together to give me a path from A to C. And then obviously we had to worry about equivalence classes because we're not just talking about paths, but it turns out that homotopies are well behaved with respect to that operation. And so therefore we get a composition that respects the equivalence class structure. And so we get a well-defined composition. And then finally, one thing that we obtain in the fundamental groupoid is that we discover that it's actually a groupoid and not just a category, essentially because every single arrow in this category has an inverse because when I look at a path, I can traverse it in either direction. So in the path P, I can go from A to B, but I can also go in the reverse direction from B back to A. And that path in the reverse direction from B back to A is the inverse to P. So this gives us a category, and it's very straightforward. I mean, it's something that we do in undergraduate courses very regularly to teach people how to show that this thing is a groupoid, or maybe, more often, we take a single point and we look at paths from that single point to itself, and we prove that the resulting thing is a group. So that's a very traditional construction, but of course, there are various things that we might want to do to that. There are some problems with this construction from the perspective of understanding the fine structure of this topological space, and that might be illustrated by this picture here, which is if I look at this example at the next dimension up. So this now is a cube with a hole in the middle of it. Well, now if I look at paths from A to B, it turns out that all paths from A to B are now homotopic to each other, because I can find a homotopy, for instance, in this case, from the path P at the back to the path Q at the front, so from this path P here to this path Q there, which circumvents or circumnavigates the hole. So in this case, I actually have two homotopies that do that. I've got one that goes up and over the central sphere that I've removed, and I've got another one that goes down and under that central sphere. So those two things are homotopic. So from the point of view of this fundamental groupoid that we built before, this is really quite a boring space. There's only one path going from there's only one arrow going from A to B and vice versa. There's not really very much information being stored inside this fundamental groupoid. And so we start to think, well, there is some extra information we could extract from this if we were careful, because of course, something to note about this is I said that there's not only a single homotopy going from P to Q, there's actually two homotopies, or well, many homotopies, in fact, going from P to Q. And in this case, I've drawn these two. I've got H, which is going up over the top of the sphere that I've removed, and I've got K, which is going down underneath. And again, these two things are in some sense quite distinct. In particular, we can think about a notion of higher homotopy. So we could talk about, I mean, a homotopy is some kind of two-dimensional path in this case inside this space. And I can think about homotopies between those two-dimensional paths. And in this case, there is no homotopy between the two-dimensional path H and the two-dimensional path K, for the same reason as before, which is that the central hole, which is in this case a sphere, prevents me from continuously deforming H into K. And we'd like to somehow capture that information because that's higher dimensional structural information about this space. So what we might have done in an undergraduate course is then talk about homotopy groups at many dimensions. So rather than just having this thing that's done with paths, we might look at higher homotopy groups done with spheres of higher and higher dimensions, and that would somehow capture this information. But another way of organizing that is to create a thing called the fundamental infinity groupoid. So in the fundamental infinity groupoid, we now again have objects which are points in the space, and we have arrows which are continuous paths between points. But now we have homotopies between those paths as kind of two-dimensional arrows in this groupoid. And we have homotopies between homotopies, I guess two homotopies, which are arrows between those. And we have three homotopies between two homotopies and so forth. So we actually have an infinite tower of homotopies between paths, then homotopies between those, and homotopies between those, and so forth. And these things all, again, have some notion of composition, because just as I could compose paths by concatenating, I can compose homotopies by concatenating, and I can compose higher homotopies by concatenation as well. And you might, I mean, we're certainly not going to do the detail of this in this talk, but you might reasonably think that I'm sort of telling some kind of truth in saying that it's possible to form this together into something that looks like a groupoid, but which isn't restricted just to, I guess, dimensions 0 and 1. So objects and arrows, we have groupoid structure actually going all the way up through the dimensions. But part of the reason I'm not going to tell you how to do this is because there is already some question about what I mean about all of that. I mean, we can certainly see what objects are and what arrows are and what homotopies are, what two homotopies are, but really understanding the properties of all of the composition operations that might be going on here is something that's a little bit beyond, well, certainly me at the moment, at this point in the talk. Now, in terms of sort of applications, because this is after all the Topos Institute, one might ask what kind of applications might I put this to? So for instance, in physics and computer science, it's common to model systems using state spaces. So we take the states of our system to be the points in a space, and somehow then the topological structure of that space tells us something about relationships between those states and tells us in particular how I can transition from one state to the next. And so paths in such state spaces represent how that system evolves through time. Each path will tell us a different path by which the system can evolve, and somehow the state space constrains that evolution. So we might take our state space and start asking questions about what paths do they have and how are those paths related. But one thing that we noticed fairly early on is that many of the systems that we're interested in are actually irreversible. So it doesn't make sense to transit along paths in two different directions because, for example, paths we hope should point forward through time. So many systems evolve through time and they only evolve in one direction through time. I mean, there are some systems which are essentially symmetrical, but many systems evolve through time. It doesn't make sense to talk about a system traveling backwards through time in here. And so therefore we might modify or put some more information on our state space to tell us a bit about the direction in which things might evolve. So I guess we have a picture like this, where now, maybe one of them is that we think of paths which are time-like, and paths will always, time-like paths only transit one direction through time, or we might think of paths in which, as we transit along the path, some kind of resource is being used up. So if we're using up a resource, of course, we can't back along the path, because that would correspond to creating a resource. So it doesn't make sense to traverse backwards through time. And in particular, what that means is that if we start looking at a thing that might take the place of this fundamental groupoid in this case, we'll find that arrows in that groupoid don't necessarily have inverses, because the inverse we had before was given by transiting backwards along the path, and that's no longer available to us. So considerations like this lead us to various notions that you'll find in the literature. One of them is directed spaces. So topological spaces that have some extra information, maybe a partial order of some kind. And these are intended to represent notions such as causality or resource use. And then once we have a structure like that, we're only going to look at paths that move in a way that is consistent with that causality or resource use relationship. So we can modify the construction that we made of the fundamental infinity groupoid. And we can now, essentially we do the same thing as before, although since I didn't explain to you precisely what we were going to do before, that's still a bit of an open question for us. But what we can do now is we can consider not all paths in that space, but directed paths only. And what happens is that, again, we get a structure which has as its objects points, and as its arrows paths between those points, and as its two-dimensional structures homotopies between those paths, and its three-dimensional structures homotopies between those. But the primary difference between this structure and the structure that we had before is that now arrows in this structure don't have things that look like inverses. There's no way for me to go backwards along a path to give an inverse. And in this way, we get a thing called the fundamental infinity category. So you might imagine that were we to emulate the fundamental infinity groupoid construction, the one where we took equivalence classes, we would get an actual category. But what we're interested in is capturing, again, that greater amount of information. And so what we're going to get is something that looks like a fundamental infinity category. We don't quotient anything out at any point. And so therefore, we get this much more complicated structure that's extending up, through the dimensions. And I claim that we may fruitfully study this thing called pi x using generalizations of standard categorical tools. So somehow I think of the paths in this space as being the arrows of a category, as we have been doing up till now. And if I think of this structure as being a category, then we might ask questions about what properties it has as a category. And we might use some of the standard tools that we have available to us, limits and colimits and functors and adjunctions and so forth, to try and study this structure.
Can I ask a question?
But of course, yep.
So is this fundamental infinity is this an infinity one category, or are there directed spaces that have fundamental infinity n categories?
So most of the versions of this that you'll find sort of hanging around in the literature, this is a fundamental infinity one category. So I guess I should say that the idea, often when we talk about infinity categories, we talk about infinity one categories or infinity n categories. Essentially, the first infinity in that says that we have, I guess, structures in this category-like structure that extend all the way through the dimensions. So we have them going all the way up to infinity. But the n tells us that certain of those structures may not have inverses. So in fact, the n says that the first n levels of that, the things in there don't have inverses. So in this case, our paths won't have inverses, but our homotopies between paths will. So this, mostly this is an infinity one category. So paths don't have inverses, but higher homotopies do. There are also versions of this in which you have more complicated things where they give you infinity n categories, but I don't want to confuse too many people with that at this point. So how do we go about actually doing some category theory inside these structures, having accepted that there are some applications for them? The other thing I should say before we move on to that is that when we start looking, as mathematicians say, in nature, which of course doesn't really mean in nature at all, it means in the papers that they've read, we discover that there are all sorts of other places where if we look carefully, these infinity categories just arise as natural constructions. So some of the things you might have heard about are things like derived algebraic geometry, which is a version of algebraic geometry that takes into account at its foundation notions of homotopy. We have formal foundations in type theory. So homotopy theory is now very important in the field of type theory. We, of course, have algebraic topology, where this all started. Areas like quantum field theory and quantum computation, because of questions around the cobordism hypothesis. And then, of course, category theory itself. It turns out that quite a number of the constructions that we do in category theory natively produce infinity categories and much more. So this is quite an important thing. I mean, understanding the category theory of this stuff is a useful thing to be doing. Now, the slogan that we tend to think about with infinity categories is we think that an infinity category is essentially a category in which we think of equality as homotopy coherent structure. And I'll try to explain that as we go through. But the idea is that somehow, when we're usually thinking about category theory, equality is just a relation between things. We say two maps are related under the equality relationship. What we're trying to do here is to loosen that a bit and to say that the interesting thing that we're going to ask about maps is not whether they're literally equal, but whether or not they're homotopic, or whether I can perturb one map into another. So it's a slightly looser, well, it's not just a relationship, because of course, as we've seen in our examples, there may be many ways of perturbing one map into another. So that was the example that we gave, where we had two homotopies between paths, one going up over the sphere and the other one going down under. So when we start thinking about equality in this slightly more permissive way, we discover that it's not just a relation, it's a structure. In the same way that we saw that our homotopies between those paths weren't just a relationship between the paths, they were really actual structures in the space. They were homotopies that looked like, in our case, sort of pieces of a flat of space. And we need to take account of the fact that this is structure in what we're doing. So if we take categories and we weaken the notion of equality, then we get a notion of infinity category. And in particular, the way we're going to weaken this is we're going to weaken equality to mean some kind of homotopy coherent structure. And I'll try and explain what that is as we go through. So you will, of course, point out that I've said, well, these things are ubiquitous, but I haven't actually defined what they are. And I'm afraid in this talk, I probably won't do that at all, just for a matter of time. But let me just give you an intuitive model of what these things, or the intuition that we're going to try and work with about what these things actually are. So an infinity category, well, we think of it kind of like a category. The first few steps of the definition of infinity category are much like we would give for a category. So an infinity one category in this case, so the one there, I wouldn't worry too much about the one, but as I say, the one says that my one-dimensional structures don't have inverses, but everything in higher dimensions do. So we start off much as we do with a normal category definition. So we say, okay, well, a category has a set of objects, that's good. Now, of course, a category has hom sets. So we have sets of maps from an object A to an object B. Well, in this intuitive model, I'm not going to just ask that that be a set of maps from A to B. I'm actually going to ask that it be a space. So it have a bit more structure. And when I say space, I'm also not going to be precise about what I mean by space, because space might mean a topological space, or it might mean a metric space, or maybe in this context, it might mean a thing called a simplicial or a cubical set. So some kind of combinatorial notion of space. But in any case, it's a coherent structure that has, I guess, which we can recognize as having clear spatial properties. We have some kind of notion that points cohere together. And one way of thinking of this in this case is as a topological space. And then the next part of the structure, again, is something that's quite familiar. So we think of having continuous composition operations. So we've got something that, I guess, given maps from A to B and maps from B to C, compose them together to give me maps from A to C. And this is done in such a way that it respects this space structure up here. So we want things, I mean, I guess if pairs of maps here are close together, then when we compose them, we want them to end up being close together in here. So all of that seems very familiar. The next part may be less so, because what we discover in our composition now is that part of this being a category with more, I guess, with a more permissive notion of identity, of equality, is that we shouldn't really be able to say that the two different ways of composing three arrows are literally equal. In fact, I mean, in this kind of world, we shouldn't really be saying that very many things are literally equal at all. Instead, what we're going to say is that the two different ways round of composing three things are at least homotopic. So if I take maps H, G, and F, and I compose them together in the two possible ways, there is some perturbation that will take one of those composites to the other, but they may not be literally equal. So I guess think of this as, if I'm given three maps, F from A to B, G from B to C, and H from C to D, then the two different ways of composing them together look like this. And I will give, as part of the structure of my category, a nice continuous map that starts, I mean, this is a point in the space KAD, and this is also a point in the space KAD. And what I'm going to do is I'm going to give a nice path. I mean, part of my structure is to give a path from this point in that space to this point in that space. And I'm going to ask that all that family of paths be nicely continuous. So that's already, I mean, what we would have had in a category was we would have just agreed that these two things were equal, and then we would have stopped our definition. Unfortunately, having not made that decision here, we're now going to have to think about, I mean, I've made some choices of structure here. I've got a choice that says, well, I'm giving some specified structure that says, here is a specified path that relates this composite to this composite. And as soon as I start choosing structure like this, I'm going to have to ask, how are those structures themselves related together? Equalities are easy, because as soon as I posit an equality, it's just an equality. An equality is an equality is an equality. Whereas having extra structure puts on us a responsibility to relate that extra structure, in this case at higher dimensions. So somewhat similarly to maybe presentations of monoidal categories, at this stage we might observe that, for instance, if we had composites of four things, then there are a number of different ways of composing those. I had a sequence of four things, F, G, H, and K. Then there are a number of different ways of composing those, of bracketing my compositions to give me composites. So in fact, in this case, there are precisely 5 possible bracketings of composites of those four things. And if I start looking at the homotopies, I mean, if I take these paths that I had here and I assemble them together into a picture, I'll notice here that, well, there's a path that takes me from K composed with H composed with this thing composed together already to this thing here, which is an instance of that where I guess I've replaced H by K and G by H and F by G composed with F. So we get a thing there. And I get a thing here, which is the opposite thing now, taking these two things as a single piece, and again, taking another instance of this. So each one of these things in this diagram around the side here is some instance of this family of paths, chosen family of paths here. And they fit together into a pentagon in exactly the same way as they do in, for exactly the same reasons as they do in monoidal categories. And I can't now ask that the two ways of composing either side of this pentagon together should be literally equal, because that doesn't make any sense in this context. And so what I ask is that there be a two-dimensional homotopy between those two sides of this thing. So I get something that looks again like the MacLane pentagon condition, but it's not a condition, it's not an equality, it's a homotopy. In fact, I've got a homotopy of homotopies. That's what we mean by a higher homotopy. If anybody says higher homotopy, it just means I've got two homotopies and there's a homotopy between them. Now, the problem, of course, is that I'm now going to get stuck in an issue of infinite regress, which is, well, I've now got some more structure, and that structure has to be taken account of at the next level up. So in my definition, I have even higher coherence homotopies. So I've got three-dimensional homotopies and I've got four-dimensional homotopies. And by that stage, I'm certainly starting to give up on this as a definition, but it certainly is a useful way of thinking about what these structures should look like. So can we formalize this definition in any way? So we can make progress on formalizing this idea with two key observations. The first one is, I think, probably a little bit subtle, which is that given composable arrows F and G in my putative infinity category structure, it may not actually make good sense to speak of the composite of those two things, because in fact, any arrow that's homotopic to that putative composite has equal right to that crown. Really, we're not interested in the specific identity of that composite. We're interested in the fact that there is some homotopy. I mean, there's a bunch of different maps that have the, that we might reasonably expect to think of as the composite. And all of those maps are going to be homotopic. In fact, more specifically, there's a subspace of all of those possible composites, and that subspace should be what homotopy theorists call contractible. And I think Emily probably talked about the importance of contractibility in this kind of thing in a talk that she gave at the Topos Institute last year. So the first thing is, we're not necessarily going to think of there being a specified composite. We're just going to have some kind of way of recognizing those things that are composites of other things. And then the second thing that we might observe is that higher associativity laws arise from the algebraic structure of higher simplices. So for instance, a two-simplex tells us something, so a two-dimensional triangle tells us something about the structure, tells us something about how things compose. So if I have a triangle like this in my space, so the idea is to interpret this as saying, well, I've got a path in my space F, I've got a path in my space G, and I've got another path in my space that I've chosen to call G composed with F. And there's somehow a nice homotopy, there's a nice sort of piece of continuous space that witnesses that these two paths have been composed together to give me a third path, G composed with F. And as I say, I mean, there may be many, I mean, I'm using the notation G composed with F here just because I need to use some notation, but there may be many different candidates for this G composed with F. Anything is going to be a candidate if there is some nice piece of space that relates F and G to that third thing at the bottom in the form of a two-simplex. So then we can look and say, well, what does the three-simplex tell us? And when we start drawing that situation, so we take a three-simplex, so a three-dimensional triangle, and we kind of flatten it out. So we take pairs of its faces and we draw two of those faces on the left and two of those faces on the right. So the idea is, think of this as sort of we've decomposed the three-simplex into two pieces. We can reassemble it by folding these two pieces along these edges here and then gluing them back together around here. You'll notice that those are labeled F, G, and H, and this is F, G, and H. So I'm actually gluing those together. And those four faces tell me that, for instance, this map here is a composite of these two things. And this face here is telling me that this map here is a composite of these two things, and so forth. And in fact, to make this a well-defined sort of simplex, I need to make sure that this edge along the bottom here that really represents I guess this says take F and G and compose them together to get this thing, G composed with F, and then compose that with H to get this thing along here. This thing here says take G and H first and compose them to get H composed with G, and then compose F on the front to give this. And to make this the boundary of a well-defined simplex, I really need to make sure that this thing is the same as that thing. I'm not really being very precise because I said to you that I shouldn't ask for two things to be the same, but the idea is that this rule here tells me something about associativity. It's the thing on the left, which is two of the faces of the three simplex tell me about the composite of these three things, F, G, and H, one way around. The faces on the right tell me about their composite the other way around, and the fact that they fit together into a simplex tells me two things. It first of all tells me that the composites both way around are related, and it also tells me that there's some kind of homotopy in the middle of that three simplex that relates this piece of witnessing data and this piece of witnessing data to those two there. So that's the sense in which associativity is a three simplex. And it turns out that the MacLane pentagon is a four simplex, and I'm not going to go through the details of where that comes from. But maybe if you read, I guess Ross Street wrote a paper called The Algebra of Oriented Simplices in the 1980s, and he has some really nice pictures and explains how it is that we extract the MacLane pentagon from the four simplex in this way. And in fact, what we discovered over very many years, I guess since the 1960s, is that the higher coherences that these things must satisfy naturally form higher simplices. It's one way of seeing them as higher simplices. So various methods have been explored to directly formalize our intuitive model, the one where we had spaces and so forth, using those last two ideas. And these give rise to a number of formal models then. So we have an intuitive model. This is kind of what we're looking for. And various people have come up with formal models to try and make that more precise. And a number of things that you'll find in the literature include things called complete Segal spaces and Segal categories and Tam-Samani categories and so forth. These are all models that were intended to, I guess, specifically, give a sort of close model of the intuition that we had, a structure with objects and spaces of maps between them. But we'll actually look at a slightly different kind of model for what we do here, which is a thing called a quasi-category. And I'll look at this really briefly because I noticed that I'm already running well behind time. So a quasi-category, which is maybe one of the most popular models of infinity category, is essentially a thing called a simplicial set. So a simplicial set isn't something we're going to define here, but essentially it's a topological, or it's a combinatorial model of a topological space that's built by gluing together simplices. So it's built by taking points and gluing lines between them, and then gluing triangles between those, and then gluing tetrahedra between those, and then gluing higher and higher simplices on to build up my space. And this is really a combinatorial model of that. And it's not really particularly important how that model works, except to say that inside that model, we can identify things that correspond to the simplices at each dimension of this structure. And the combinatorial structure tells us how those simplices are related one dimension to the next. Now, the way that so we take a simplicial set and we say that a quasi-category is something which is a simplicial set that admits things called fillers for inner horns. And rather than defining for you precisely what that means, I'll just show you the first couple of examples. So a filler for, I guess, a two-dimensional or one-dimensional horn in this case. So the horn looks like, in my simplicial set, looks like just a pair of edges. So the one-dimensional structure of this simplicial set, they're just directed edges. So I take an edge called F and I take an edge called G, and that thing together is called a horn. And the reason it's called a horn is it kind of looks like this picture here. I've got, I guess this is the point that I blow into the horn, and this is the bell where the sound comes out here. It's a simplex where I've thrown away the top dimensional data of the simplex, and I've also thrown away one of the other faces. So I've got no simplex filling in here, and I haven't got this face here, but these are the remaining two faces. So I've got F and G. That's the input data to some kind of operation. I want to compose them together. And the way I compose them together is I do a thing called filling. So somewhere inside my combinatorial simplicial set, I posit that there is a 2 simplex starting with F and G, which gives me both a K, which I think of as the composite of F and G, and gives me a 2-dimensional simplex here, which we think of as the homotopy. That homotopy is a piece of data that states K should be regarded as a composite of G and F. Now, I guess I should probably, now, I'm not making any assumption that that's unique at all. So there may be many simplices that can fill this in this way. So there may be many ways or many different simplices that have as their top 2 edges F and G, but which might have a different K and a different twiddles filling it in. We're not asking for uniqueness at all. We're just asking that such a thing exists. So a composite of F and G exists, but there may be many such things. And then at the next level, at the 2-dimensional level, this is what a horn looks like at dimension 2. So again, a horn looks like a simplex where I've thrown away the top dimensional information. In this case, that's the 3-dimensional information. And then I've also thrown away one of the other faces. So in this case, I've got this thing here has all of the information that I might normally have in a 3 simplex, except that it's missing this face here, and it's missing the top dimensional information here. It can't have that top dimensional information there because for that to be there, I'd need to have that in here. And the filling process says that somewhere in this simplicial space, there is actually a genuine, in this case, 3 simplex that has all of this data as various of its faces, but adds for me the extra data of something here and a homotopy in here. So what this something here does is it witnesses that the composite, or it witnesses that L can be regarded as some kind of composite of H and K. And so again, what this filling process says is essentially, if I start with some composite of F and G on this side, call it K, and I start with some composite M of G and H, and then another composite L of F and M, then on the other side, I can find a thing in here that witnesses that I can regard L also as a composite of K and H. Okay. So one of the reasons for explaining this at this point is just to explain that, well, this is already far too complicated for, without some extra technology, trying to do category theory with this kind of structure is going to be a little bit confronting. Okay, so at this point, we now have some, arguably far too many, formal structures that claim to model our intuition about infinity categories. But we promised to do some category theory with them, so how might that work? And in particular, we might ask, well, how can we do things like limits? And if we're thinking of whatever these structures that we've just been talking about are as categories, then we might ask questions like, what do limits and colimits look like in those categories? Or can we form comma structures? Or can we do adjunctions? Or can we think about monads in this context, or Grothendieck fibrations, or toposes, or Yoneda's lemma, and so forth? So in principle, what I should do is I should go through, and I'm certainly not going to do it here, and explain to you, maybe pick one of those models, quasi-categories possibly, and explain to you how each one of these things works in that context. And essentially that process would be a translation process. I'd think carefully about how it worked in the category context, and then I'd try to see how I can translate it across into this more complicated context. And sometimes that works relatively straightforwardly, and we can see that the concept we get in this, in some of these strange models is the same thing as the concept we started with. Other times that coding is a bit more complicated. But if you wanted, for instance, to find out how all of this was done just in the case of quasi-categories, then you might go to Jacob Lurie's famous book on higher topos theory, and he certainly explains all of these structures. So all of these structures can be found in that work. And he does in very great detail how those work just in the quasi-category model, not in any of the other models. So one question we might ask is, what model should we use? And certainly Jacob Lurie's decision was to use the quasi-categorical model. But what I'm going to suggest is that maybe we might take a different approach, which is, let's not pick a favorite model at all, or let's try and avoid picking a favorite model. Well, so when we started thinking about this many years ago, I was indulged because I'm an Australian category theorist. And so I was humored by allowing for the idea that we might try to do some of this stuff too categorically. So in Australia, I guess we've been worrying about two categories for many years, since the 1960s. And our primary interest, certainly in the 1970s, was to understand how category theory itself could be expressed inside a two category. So a two category is a category that has objects and has arrows between those objects, and then has arrows between those, which are called two cells. So we think maybe, I don't know, the category of categories is such a thing, because we have categories and we have functors, and then we have natural transformations between those. So we get some kind of two-dimensional category structure. And it turns out that we can develop a very great deal of abstract category theory just in the context of that two category of categories. And this is something that Australians are rightly proud of having done over many years. So maybe one approach would be to try and appropriate some of the things that Australians have been doing with two categories into this context. And I have a little cartoon that explains what we might want to do here. So the first thing you might think is, okay, well, I mean, that's great. Categories form, I mean, if I take categories and I take functors and I take natural transformations, they form a two category in a very natural way. But now if I take something like quasi-categories and I take the functors between those, and then I take the natural transformations between those, well, there's now all sorts of higher structure here, because there are homotopies between natural transformations and homotopies between those and so forth, because of course, everything's homotopies all the way up. So this is already starting to worry me at the point that we started to discuss this, because this means that I'm going to have to invent something called an infinity two category. So some kind of infinity categorical notion that is like our infinity one categories that we already don't really understand very well, and is also like these two categories, which maybe Australians understand quite well, but we might be a bit leery about generalizing them too much, and that sounds hard. But it actually turns out that we can do much better than this. We can at least make things a bit simpler by using a semi-strict model of such things. And in fact, the semi-strict model that we picked is a thing called quasi-categorically enriched categories. So they're strict categories that are enriched in the traditional sense of the word. Every single hom is an object in some other category. And what's more, we have a composition operation which is strictly associative. And so these are relatively simple structures to define and to use, and certainly was something that we felt that we could deal with. And so we set to work. And technically speaking, what we got a thing called an infinity cosmos. So an infinity cosmos is, I mean, it's called that because the kinds of structures that they're modeled on were called cosmoi by Ross Street in the 1970s. And technically speaking, these are categories of vibrant objects enriched in the Joyal model structure. So that doesn't matter. What it means is that these are structures that have objects called zero cells, and they have arrows between those objects called one cells, and they have arrows between those called two cells. And then those two cells are related by higher homotopical information that's identical to the kind of stuff that we were talking about earlier on. And we can compose these things in two different ways. So we've got a horizontal composition that's just nice, straightforward, associative composition that we're all very familiar with. And then we've got vertical composition that is now done using the sort of quasi-categorical filling method. So at least in the horizontal direction, this is a nice simple structure to work with. But in the vertical direction, it's still a little bit more complicated than we might hope for. But it turns out that for a surprisingly large range of purposes, it suffices to work in a quotient of this kind of structure called its homotopy 2 category. So the idea is that we kind of cheat a bit, and we do what we did with the infinity 1 groupoid right at the beginning. We take homotopy classes of things. So the homotopy 2 category of one of these cosmoses has, as its 0 cells, the 0 cells of the cosmos, and as its 1 cells, the 1 cells of the cosmos. But now what we do is for its 2 cells, because those had a complicated vertical composition structure, we take homotopy classes of those. And just as before, what that does is that now makes, once I take homotopy classes, I now get a nice, strictly associative vertical composition of these 2 cells. And what I get is I get a genuine 2 category. So anybody who's happy with genuine strict 2 categories should be happy at this point that they might be able to work in this kind of structure. Of course, interestingly, when I've given this talk in various other contexts to infinity category theorists, they're often very happy with infinity categories, but less happy with 2 categories, which I think is probably the wrong way around, but never mind. So this is a good old-fashioned 2 category, and we might ask the question, what do we get if we study standard 2 categorical structures in this homotopy 2 category? So a very quick case study I can give you is the case study of adjunctions. There's a very well-known notion of adjunction in a 2 category, and it's just given equationally. So to give an adjunction in a 2 category, for instance, in cat, we simply give a pair of 0 cells, a pair of objects, A and B, and we give a pair of functors or 1 cells between them, U and F, and then those have to be related by 2 cells called the unit and the co-unit. So the unit goes from in this case, from the identity on B to U composed with F, and the co-unit goes from F composed with U to the identity on A. And notice that I put square brackets around this for the moment because our 2 cells in our homotopy 2 category are equivalence classes of 2 cells in the original thing. And then those things have to satisfy the famous triangle identities. And we know from experience in category theory that this is a complete characterization, algebraic equational characterization of adjunctions. And what's more, this thing satisfies all of the basic properties that we'd expect from adjunctions. So we can certainly play this game inside this homotopy 2 category, but by doing that, we might find that we don't get an interesting structure at all, except that in this case, rather remarkably, it turns out that when interpreted in various of the infinity models that exist, so all of those things, quasi-categories and Segal spaces and complete Segal spaces and Segal categories and so forth, when we interpret this very simple notion of adjunction inside the corresponding homotopy 2 category, we find that this notion coincides with all of the other notions of adjunction for infinity categories that exist in the literature. And in particular, in quasi-categories, for example, such adjunctions are characterized by some kind of higher universal property, which can be expressed as a Horn filling property, which I won't explain, but which I've drawn in the slides for you later on. So that very simple equational notion translates into something that looks very similar to the kind of filling properties that we were using for describing composition in the quasi-category. And not only does this have a sort of basic version sort of at the level of the 1 arrows inside this structure that we might be familiar of, this looks very similar to the universal property that we usually have in a category. This is also comes equipped with higher versions. So there are versions of this notion of universal property that exist at all dimensions going up, which is a somewhat surprising thing because the equational definition that we gave inside the homotopy 2 category was somehow just two-dimensional. It was, I've got 4 things and I've got 2 equations, and it was very straightforward, sort of two-dimensional. But what we get out of that when we interpret it in these structures is we actually get all of these higher dimensional universal properties that we might want. In other words, this is the right notion of a junction, even although it's very, very simple in this. I mean, we've done some kind of terrible thing, which is you've taken an infinity 2 category, we've done massive damage to it by quotienting it out to give a 2 category. Then we've taken a notion that should not be at all related to a junction, in sort of infinity adjunction in this context. We've interpreted it and discovered it's the right thing. That's a kind of remarkable thing to do.
Dom, I'm sorry,
Yep.
but I only have 5 minutes now, and you're already to the
Yep.
question period time.
Okay. So it turns out that this is the right notion of a junction. And if we start doing 2 categorical proofs with these things, we get valid proofs about those junctions, of course. But we often get proofs that are much simpler than the infinity categorical ones that you might find in the literature on specific models. So, I mean, for instance, just looking at what adjunctions are, the definitions are complicated in a lot of those places. And what's more, the proofs with those definitions are complicated and sometimes a little bit unintuitive. So maybe I'll just conclude on saying how much can we capture in this way? So it turns out that we can capture theories of limits and I mean, this is sort of in this way working with these notions inside these homotopy 2 categories. So we can capture notions of limits and colimits, of comma infinity categories, of adjunctions, of growth and deep fibrations, of pointwise Kahn extensions, and we can do Yoneda lemma. So those are all things that reduce to essentially the 2 categorical proofs in those homotopy 2 categories. We can also, with a little bit of extra 2 categorical structure, handle things like pre-sheaf categories and toposes or infinity toposes in this context. You might also ask, what do we do about monads and monadicity? But it turns out that the monad study can't entirely be undertaken inside the homotopy 2 category because it needs a homotopy coherence result for adjunctions, which I can't explain in this talk. But once we have that, then we can emulate the proof of Beck monadicity, for instance. So Beck monadicity is expressible in the homotopy 2 category, and we can prove with this extra homotopy coherence result that it gives us the right thing, that it tells us what the monadic adjunctions are. And I think I'll stop there. I had hoped that I would tell you a little bit about type theory, but maybe I might encourage you to invite either Emily or I back to tell you about how we can do all of these things rather remarkably in homotopy type theory. So thank you very much, and thank you for your indulgence letting me speak for a few minutes too long.
Thank you very much. That's been really great. I don't know if you have the chat on. Can you see the chat there? There's
yes, it was going a bit too fast for me to monitor while I was talking. So I'm sorry if I didn't answer questions as we went through.
I think you're right. I think, you are in the flow, you're explaining things, you're in the middle of things. It's better to kind of come back to it. If people want to, they can. And I'm kind of looking to hands. I cannot see them at the moment. So yeah. They should be on the top, right? If they. So do we have questions apart from the things that are in the chat?
Yeah, I have my hands up, but maybe you can't see it. So
I can't see it because I'm incompetent. But go ahead, Tim.
That's fine. First of all, thanks for the great talk. It was super exciting to me. I'll ask a really naive question, which is that, like, throughout this talk, something that I don't know if I found it reassuring or worrying, but like you seem as well like quite surprised that sometimes this 2 categorical stuff is enough, that somehow like things work. And this is something I've never really understood. I'm one of these people who is much more comfortable with the number infinity than the number 2. Like 2 categories really scare me. So like, is there some, I don't know, like, is there some good moral justification for, like, why don't you need to do 3 categories? Like, why is 2 somehow enough? You know, I know this is a very big, vague question, but hoping you can say something to, I don't know, reassure me.
So I'd have to say that maybe, so Emily points out in the chat that in the cartoon that I drew of us, the last frame of it is that she's drunk her coffee and I still have, famously, when we drink coffee together, she always drinks her coffee early and I leave mine until it goes cold. And it was probably in one of those discussions that we were both surprised by the fact that somehow this quotient, like interpreting things like adjunctions in this quotient, was at all an interesting or useful thing to do. So, I mean, to us originally, I think it was quite a surprise. I think, I mean, of course, at least some of this is not deep philosophy. It's looking in specific models and asking the question, what actually, when we look at these structures in here, what actually happens? Fundamentally, what it comes down to is that it turns out that things that can be characterized by universal properties can probably be expressed in the homotopy 2 category context, because there's enough information being stored there to give us, for instance, the theorem that says from an equationally defined adjunction, I do get all of the higher homotopical universal properties that I need. Things that require, however, equational data, that's not going to work there. So this is the reason why it works for adjunctions, but it doesn't work for monads. So if you take a monad in the homotopy 2 category, that is not the same thing as a homotopy coherent monad. It's not the right notion. The reason that we can go backwards and forwards between those things, well, the reason that this is at all useful is that starting with an adjunction, it has the right universal property, the infinity categorical universal property. And using that universal property, I can then build up for that adjunction all of the higher coherence data. And this is sort of common in, even if we look at adjunctions or bi-adjunctions between bi-categories, the relationship, the existence of the unit and co-unit and the triangle identities are enough to characterize the universal property. But we know that when we start using that universal property, we then have higher coherences. So we have this swallowtail axiom that comes out there. So again, the reason we can rebuild that for an adjunction is because that's built from the universal property for which the first 2 layers were enough to specify. So, I mean, certainly my philosophy on this is if it's a universal property, I can express it in the homotopy 2 category. If it's something equational, then I'm going to have to prove a homotopy coherence result. The other thing I should say is that a lot of this, certainly in my mind, is modeled on, at the next dimension down, on derivator theory, where again, there are certain things we can do in the homotopy category, but so a bunch of things that we can express in the homotopy category of a model category. But to get the full theory, we need to do something a bit more. So sometimes we need to prove a coherence result in derivator theory. So, I mean, one way of thinking about this, probably not for most people in the audience, is that really what we're looking at is some fragment of 2 derivator theory here. And so in the same way that derivator theory suffices to tell us about universal properties, that's really what's going on here. But again, in derivator theory, if we've got something that's equationally defined, I've got to sit down and do a homotopy coherence proof about it. Yeah.
That's a nice, good, yardstick or whatever to have, this idea that universal properties means it's probably going to pass through in this thing. Yeah. Okay, thanks. That was helpful. Thank you.
But that doesn't kind of make a difference between 2 and infinity, does it? I mean, because, what is kind of bothering me with this explanation is the fact that monads have equalities. I mean, you define them through equalities on the triangles, but the adjunctions do the same. So why such a big difference?
So I guess, So there's a bit of a trick going on in this, which is that although the equationally defined adjunction is it's an equationally defined structure in a 2 category, that I can test information inside that by looking at maps out of other things in that 2 category into it. And those other things allow me to express arbitrarily complex shapes inside the categories on either side. And that's what allows me to show that an appropriate universal property holds for these. Unfortunately, that technique doesn't work for something like a monad, essentially because the monad isn't defined as a universal construction. So it's sort of, I guess the status of equationally defined adjunctions, again, maybe the remarkable fact is that adjunctions can be defined both universally and equationally. And maybe we shouldn't be expecting that. It just happened. We got told that early enough in our categorical education that we just accept that. But maybe that's something that we should be a little bit more suspicious about. Maybe that's something I should have been more suspicious about when Pino Rossellini taught me about adjunctions when I was a child.
Indeed. Can I ask a kind of a very quick run through what you would have said about type theory? Oh, sorry, there's someone else who's also asking a question, but sorry, who's the Zoom user who's trying to ask a question?
Lee Munshine, but don't let me interrupt your question.
Yeah. Right. Please. So my question is this business of how do we kind of well, actually, I don't remember my question. So carry on with your question.
Okay. So briefly, thank you for this beautiful talk. It's been most illuminating for me after listening to a lot of related talks. My question is this: I come currently from my interest in category theory from the point of view of what I might call the semantics of biological processes. You know how control signals are developed in the context of biology, and how the control of control evolves. Everything about biology is all about the evolution of higher and higher levels of control. And so I look at, infinity categories as kind of my, how should we say, hopeful arc on which to float into this biological domain. My question is, do you and your fellow wonderful Australian categorists have interest, in applying this theory in that context in which we're trying to model basically the higher order semantics of biological processes, if that term makes any sense to you?
Mm-hmm. I obviously can't speak for my colleagues, although, I should say that one should always admit one's faults, and maybe one of our faults here in Australian category theory is we are terribly abstract.
That's good.
And we tend to concentrate on the abstract rather than the application. Certainly that is something that we're interested in, or certainly I personally am interested in. But as yet, I don't really have any particular handle on how to get it to work in the infinity categorical context. It's not. I know that I guess sort of work that I have pondered categorically in the past with maybe stuff that Robin Milner did on some of these questions, and sort of his categorical presentation there. It does seem to me that there are some aspects of that could be put into this kind of a framework, but I don't have I'd love to have more of a chat with you sometime offline about that, because it's certainly something I'm very interested in, but really don't know a huge amount about.
Thank you.
Okay, I think I kind of remember what I wanted to ask about, but I think it's might be too involved for now. So I think maybe we should stop the stream and thank the speaker again, and then we can, people who want can carry on chatting a little bit more to Dom about this wonderful talk. Thank you.